In this first tutorial, in this second workshop, I'm going to provide a crash course in linear mixed effects modelling. We're assuming here that you already have some basic understanding of linear regression models. And what we want to do is try to build on that to show how those relatively simple regression models can be extended to dealing with multi-site data. So to begin with, we're going to look at data from a single sampling location, apply a linear regression model to it, and look at some of the limitations of that approach. We're going to build on that then to look at why we might want to extend our data set to consider information from multiple different sampling locations and look at the advantages and challenges that that brings. Then look at how we can use linear mixed effects models, a slightly more sophisticated kind of regression model, for analysing spatial temporal data that comes from different sampling locations. And then finally, I will briefly signpost you to some more advanced statistical techniques, which you can use and give you broader flexibility for working with different kinds of data. I would just like to emphasise that this is very much a crash course. The aim really is just to give you an initial understanding of how some of these techniques work, just to provide a foundation then for looking at how we can use the HE Toolkit to apply those techniques. We don't unfortunately have the time available within this workshop to go into a lot of technical detail. If you are interested in using these approaches, however, I would strongly encourage you to do some additional background reading so that you understand a little bit more about the mechanics of their techniques and how you can apply them in an appropriate way. I'll be signposting you to some additional resources which can help you with that at the end of this workshop. I should also just emphasise that just to keep things simple, we're going to be looking at linear mixed effects models which assume your data follow a normal distribution. And we're also going to be dealing with relatively simple models where we allow the slope of our hydro-ecological relationship to vary from one location to another. You can again extend these models to include more complex, nested and crossed random effects, but again, that's something which we won't be covering today. So let's start off by looking at some real-world data. Here we have a time series of data taken from a long-term monitoring location on the River Derwent in Derbyshire. The red points represent individual macroinvertebrate samples. So we've got a data set here which spans a 20-plus year period. These red points represent macroinvertebrate samples, as I said, and we've represented the invertebrate community here using a life score. So a life score is a community level index which describes macroinvertebrate responses and in response to habitat changes that arise from fluctuations in river flow. So essentially higher scores indicate that we've got a greater variety of species and higher abundance of species such as mayflies, stoneflies and caddisflies that prefer high velocity conditions and clean substrates. And lower scores indicate a community with a greater abundance and prevalence of species that prefer sort of slower, silty water and more silty substrates. So that's species such as beetle, larvae, leeches, and snails and so on. Here, the life scores are actually represented as a ratio of what we would expect under minimally impacted reference conditions. So that OE ratio means that higher scores indicate a more healthy invertebrate community and lower ratios indicate a community which may be showing signs of flow stress. Not only do we have the red points on the time series plot, but we also have some hydrological information. So here we've got daily mean flows from a nearby gauging station. So we have both ecological and hydrological information on the same graph. And what we're interested in trying to assess is whether there's any association or correlation or relationship between the flows and the invertebrate life OE ratios. But when you plot up the data in this way, it's really quite difficult to just eyeball it and determine whether or not there are any relationships there. Things become a little bit clearer when we summarise that relatively high resolution, that daily flow data. As we looked at in workshop 1, we can use the calc flowstats function from the HE toolkit to summarise the flow data and boil it down into a more useful and concise summary statistic. Here we've used a 12-month moving window, and for each moving window we've calculated the Q95 flow, that is the flow that's exceeded 95% of the time. We then standardised those Q95 flows. This means that those standardised variables have a mean of 0 and a standard deviation of 1. And this is a useful way of making these kinds of flow summary statistics comparable across different sites which might be on different sized watercourses. These standardised Q95 values, if they're greater than 0, it indicates that the Q95 is higher than normal for that site, and if it falls below 0, it indicates that the Q95 is lower than normal for that site. We've chosen Q95 because it's a commonly used measure of low flow conditions at a given monitoring location. We could, of course, use different flow statistics, but just for the purpose of illustration, we're just going to focus on Q95 as a relatively simple, commonly used statistic. If we look at the blue line on the graph now, we can see that time series of standardised Q95 values does a much clearer job of picking out the hydrological variability at this site over our 20-year time period. In particular, you can see that the blue line dips, indicating low flow or drought conditions. So it picks out the 1995-6 drought quite clearly, a further drought in 2004, and another one in 2011-12. Equally, you can see it also picks out periods of time when flows have been substantially above the long-term normal for this situation for this site. Now, if we eyeball the data, you can start to see at least a hint, I think, that there could be a correlation or association between the life scores and the hydrological conditions that have prevailed at different points in time. There seems to be a tendency for the red points to go down during periods of lower than normal flow and to go up during periods of higher than normal flow. And we could try to formally quantify this using a hydro-ecological model. And to do that, we seek to regress the life scores against our standardised Q95 values. And that's what's shown on this next slide. So now you can see that the Q95 values are on the horizontal axis at the bottom, and the life OE ratios indicating the health of the macroinvertebrate community are on the vertical axis. Each black point represents a particular point in time when we have a macroinvertebrate sample, and it tells us what the Q95 flows were like in the 12 months prior to that invertebrate sample being taken. So it provides a measure of the antecedent flow conditions that those invertebrates have experienced prior to that sample being collected. A simple linear regression model really seeks just to define a line of best fit for our data, a simple straight line, and that's shown on the slide here by the black line. What's interesting here is that black line has a positive slope. That tells us that there's a positive association. So when the flows at this particular location are higher, we tend to get higher life scores and vice versa, which is what we would expect typically. As a general rule of thumb, higher flows more often than not tend to be beneficial for the ecological community. To fit this kind of model in R, we can use the LM function. This fits a linear model. This function is part of the base R setup, so you don't need to install any packages to run this. You can see here the syntax we use to define the model formula. So on the left-hand side, we have our response variable life. We then have a tilde, and then on the right-hand side, we have our predictor variable, which in this case is the Q95Z, standardized Q95 value. This linear regression relationship is defined by two parameters, alpha and beta. So the model formula is shown on the slide here in red. So essentially, we're saying that the predicted or expected life score is a function of alpha, which is an intercept value. This is the mean value of our life scores when our response variable is 0. Here our response variable is standardized, so a Q95 value of 0 indicates that our low flows are normal for that site, and so the alpha coefficient tells us what we would expect the life scores to be under those conditions. The beta coefficient describes the slope of the line. The steeper the slope, the more sensitive our ecological community is to antecedent flows. Formally, the beta describes how much the predicted life scores change in response to a 1 unit change in our predictor variable. So in this case, if our standardized Q95 flow increases from 0 to 1, or from 1 to 2 by 1 unit each time, then we will see the same constant change or increase in our predicted life score. So when we fit a linear regression model to the data, essentially we were asking the model to estimate these two coefficients. So we can see here on the slide that our intercept is estimated to be 1.03. So that's the life score under normal flow conditions. And the slope is 0.016. That describes how much life score changes on average every 1 unit change in our standardized flow statistic. Now this is possibly the simplest kind of hydroecological model that you could build. We've got data for one site, we've got a single predictor variable, and we're assuming a straight line relationship. It's not a bad model. We can certainly build on it. We can certainly make this model more complex if we wanted to be, by, for example, including predictor variables to describe other aspects of the flow regime, or maybe incorporating other variables to represent flow conditions more than 12 months prior to sample collection. We can see that the black points, the actual observed values, there's a certain amount of scatter around the regression line, so that it's indicating there is an appreciable amount of unexplained variation still left in the data. But the basic point here is that we've used a statistical approach to define a regression relationship, and we can use that relationship to make a quantitative prediction of what the life score would be, what we would expect the life score to be on average under any particular flow condition. And from that we can then estimate how much we would expect our life scores to change and if the flows were to change at this location as well. Now, we've applied this model to data for single sites, and this site is actually relatively well sampled. We've got 29 invertebrate samples over a 20+ year time period, and so that gives us a reasonable chance of being able to detect at least a sort of simple hydroecological relationship. But we need to be very careful in applying this kind of approach to sites which don't have as much data as that. Experience has shown that you need a surprisingly large amount of data to be able to describe hydroecological relationships, and particularly to be able to start testing or disentangling the influence of different aspects of the flow regime. So just as a little bit of a sort of a cautionary tale, on this next slide I've just done a very simple simulation exercise. In the top left-hand corner there, you can see we've got the full data set that we were just looking at, all 29 samples. But in the other 8 data sets here, those are each a reduced version of the full data set, where I've randomly selected 8 samples from the full data set. So these 8 reduced data sets essentially represent sort of the sorts of data that you expect to see from a site which is not as well monitored. And when we fit the same linear regression model to each of those reduced data sets, you can see, as you might expect, that the estimated regression line shows a lot more variation in the slope, first of all. So data sets, for example, 4 and 6 and 9 have a much weaker slope than the full data set. So they're tending to probably underestimate the true hydroecological relationship. And conversely, for example, data sets 7 and 8 show much steeper relationships than the full data set. So those are overestimating the strength of the relationship. If you look at the grey shaded area around each regression line, that's a confidence interval, and that tells us how certain or confident we can be about that relationship. And again, as you would expect, when we're looking at the full data set, that confidence interval is relatively narrow, indicating we have good confidence about the shape of that relationship. But in each of the reduced data sets, that confidence interval is much wider, indicating a much greater margin of error and lower confidence about the exact form of that hydroecological relationship. So this is really just a way of illustrating that if you're trying to develop regression models for monitoring locations which have relatively small amounts of sample data, you do need to be very careful and treat the results with quite a large pinch of salt. As you can see here, whilst you can fit a regression line to the data relatively simply, that regression line may not provide a very useful or meaningful representation of the hydroecological relationship. There's simply not enough data for us to tell really clearly what's going on. Evidence of working with these kinds of data sets suggests that ideally you need at least 15 years worth of data, and that those samples or surveys need to be collected over several different sort of wet and dry periods to give us a good sort of basis, if you like, for trying to understand how flows influence the development and changes in the ecological community. So what can we do if we're faced with a situation where we don't have as much data as we would like? Well, the obvious thing to do is to draw together or pool data from several different sampling locations. So rather than trying to fit the model based on data for a single site, we use data for multiple sites. That gives us a larger, richer data set and a greater potential or possibility for defining a useful hydroecological model. But we need to be very careful when we're using data from multiple sites. There's various different ways which we could seek to analyse that data. What we shouldn't do is just take data from multiple sites and throw it into a simple linear model of the kind that we've just looked at here. If we do that and completely ignore the fact that the data has come from several different sites, then we will get very misleading and potentially unuseful hydroecological models. What we can and should do is actually acknowledge the fact that the data comes from several different separate sampling locations. So on the slide here, you can see now we've got data not from one site, but from 4 separate monitoring locations, all in the same catchment. The site we were looking at is in the top right-hand corner here. So you can see the strong positive relationship that we've just observed. We now have 3 other sites in our data set as well. 2 sites at the bottom also have a relatively good amount of monitoring data. The site in the top left-hand corner is relatively data poor. It's got many fewer samples. Now, we could fit a linear regression model to this data set using the formula that you can see on screen here. So we could fit an LM model where we're seeking to model the response of life as a function of the standardized Q95 statistics. And here we include an interaction with site. So we're telling the model that the data have come from 4 different sites, and essentially we're asking it to describe a separate linear regression line for each of those 4 sites. So both the intercepts and the slopes of those lines can vary from one site to the next. And again, you can see on the slide here, this model essentially estimates a separate intercept and slope for each site. What's interesting to see is the variation we get in those fitted regression lines across the 4 sites. Our original site has a relatively strong positive relationship. Our second site here in the bottom right-hand corner actually has a fairly flat relationship. There doesn't really seem to be any influence of antecedent flows on our life scores. The third site has another positive relationship, which actually appears to be steeper than our first site, but you notice there's also quite a lot of scatter in the points around that line. And the 4th site in the top left-hand corner, this is the data poor site. And this intriguingly shows actually a negative relationship. It's suggesting that higher flows actually lead to lower life scores. And that runs counter to the evidence that we're seeing from the other sites. Now, this approach works fine if we want to directly sort of compare and contrast these four sites. So if, for example, we want to know whether site A has a steeper slope than site B, for example, then this kind of model is a very appropriate way of doing that. And we can formally test these different slopes and intercepts to see how these four specific sites sort of measure up to each other. However, this modelling approach, a standard linear regression model, means that the confidence intervals will still be uncomfortably wide for individual sites which are relatively sort of data poor. So that site in the top left-hand corner, we still have a high degree of uncertainty really about what the hydro-ecological relationship there looks like. This approach is also relatively inefficient from a statistical point of view because we have to estimate a separate intercept and slope for each site. So that gobbles up lots of degrees of freedom and means that we have a slightly reduced power to detect statistically significant patterns in our data. A third limitation is that whilst we can describe the hydroecological relationship for each individual site, all these sites have a different slope to them. So there's no basis here for generalizing which would allow us to make predictions, for example, for a new unmonitored location. For that new location, we don't have any basis for saying whether it would be respond most similarly to site A, site B, site C, or site D. So we can't generalize. We can only make inferences about these four specific sites. So what we need is a slightly more flexible statistical regression method, which will allow us to sort of generalize and define an overall hydroecological relationship based upon this multi-site data set. And that's where linear mixed effects models come in. Here we've got exactly the same data set. The black points are the actual measured data. The black line is the slope of the relationship for each individual site, as we just saw on the previous slide. Now, however, we're going to use a linear mixed effects model. To do that, we use a function called LMER. So it's a linear mixed effects regression model. The formula is very similar to that which we had on the previous slide for the standard linear model. We define our response variable first, that's our life scores. Our flow predictor variable is the standardized Q95. We also have site variable in the model as well. Now we allow this flow effect, the Q95 effect, to vary from site to site. You notice it's in brackets and we've got a bar between the Q95 and the site. That tells the model that this is a random effect. We want to allow the effect of flow to vary randomly from site to site. Essentially what the model is doing here is it's taking the data for the four sites and it's pooling it together to define a global relationship. You can think of it as averaging, in a sense, the intercepts and the slopes for the four sites. But it's a weighted average. It gives more emphasis to those sites which have either a lot of data or more tightly defined, less noisy relationship. So you can think of this really as providing a best estimate of how macroinvertebrate communities in these types of streams respond to changes in flow. That's shown by the blue dashed line on the chart here. So we're fitting, if you like, a global or a common relationship across all four sites. And we call this a fixed effect because it's common to all four locations. Now, obviously, this only really works when we are taking data from sites which are hydrologically and ecologically similar to each other. In that situation, we can reasonably expect there to be a sort of common underlying relationship which applies to all of the sites in our data set. So the mixed effects model goes a step beyond the standard linear model because it provides a true estimate of this underlying or common global relationship. However, it gets better than that. Because not only does the mixed effects model give us an estimate of this global effect, but it then takes that global effect and it adjusts it to reflect the data for each individual location. This essentially is, if you like, a sort of a hybrid or blended approach. You can think of it as taking the global relationship and then adjusting it to the data for each individual site. this gives us a regression relationship for each site, which reflects both the data for that site, but also is influenced by the whole data set, if you like. The orange line, therefore, is what we call a mixed effects estimate. It's a blend of the global relationship and the site-specific relationship. You can see if we look at the data for the 4 sites here, that blended relationship, the orange line, is actually quite close to the black line for 3 of the 4 sites. So the 3 sites which have relatively large amounts of data and therefore relatively clear hydroecological relationships, that the orange line is actually pulled quite close to the data for that site. But for the 4th site in the top left-hand corner here, where we have relatively few samples and therefore a lot of uncertainty about what the site-specific relationship is, there, the orange line is much closer to the global relationship. Because there's not much sample data for that site, the mixed effects estimate isn't heavily influenced by the data for that site, and so it stays close to the global relationship. So another way of thinking about it is that the site-specific relationship is pulled towards the global relationship, and it's pulled more for those sites which are data poor or have very weak relationships. And that tendency for the site-specific relationship to be pulled towards the overall global relationship is called shrinkage. So as I said, this approach works well where we can identify and analyse data from a set of sites which are hydrologically and ecologically similar. What this ultimately yields is again a regression line for each site, as shown in the bottom right-hand corner of the slide here. We get a separate intercept and slope. That's a blend of the site-specific data, also borrowing information from the whole data set. Just to take a step back and summarise that then for a moment. Linear mixed effects models are basically an extension of simple linear models, and they include one or more what we call random effects, which is typically a grouping factor such as site. So site is a factor because it's categorical. We have data from several different discrete monitoring locations, and it's called a random effect. It's a slightly confusing term because essentially it means that we're interested in trying to describe the variability from one site to another. The goal of these models is really to try and define a sort of an overall relationship for our data set. We could conceivably have undertaken the same analysis using data from a different set of sites, and we basically conceive of these sites as being drawn from a wider population of possible monitoring locations. The model actually fits a global relationship, which is shown on the slide here with the blue dashed line. And then, as we saw on the previous slide, that global relationship is then adjusted for each site. We can make that adjustment in 2 different ways. We can have a model which has just random intercepts, as shown on the top of the slide here, where the global relationship is adjusted up or down for each site. The slopes remain the same. Or we can have a model which has a random intercept and a random slope, as shown at the bottom. Here, the global relationship for the whole data set is adjusted so both the intercept and the slope of that line can change and be variable for each site in our data set. So the random intercept model accounts for differences in mean status, our mean biological metric from site to site, whereas the random slopes allow the slope of that relationship to vary as well. So essentially that gives us a way of modelling different sensitivity to flow at each location. So the strength and direction of the hydroecological relationship can vary from site to site. In a mixed effects model, when we estimate those random effects, we assume that they follow a normal distribution with a mean of 0 and a variance sigma. Here we treat that variation in the response from site to site not as a source of nuisance variation, but it actually becomes an integral part of the analysis. We can actually quantify as a variance how much the intercepts and the slopes vary from one location to another. So in the top diagram, for example, we can see that we have 3 different intercepts, and we can just, if we assume those follow a normal distribution, then we can quantify that variability from site to site as a variance. Similarly, we can, in the bottom diagram, we can quantify the degree of variability in the intercepts and in the slopes. Now we actually have a basis for understanding how consistent or otherwise those hydro-ecological relationships are from one site to another. High variances would indicate lots of variability, so each site is really sort of doing its own thing, whereas low variances would indicate all the sites are showing a very similar hydro-ecological relationship, so they are more similar and less variable. Let's then just sort of summarize really some of the strengths and weaknesses of these linear mixed effects models. Starting with the strengths, so these models are generally more robust. By pooling data together from multiple different sampling locations, they allow us to estimate hydro-ecological relationships more precisely. And that is particularly beneficial for data poor sites, where we are able to borrow information from other sites in the data set to give us a more precise, more confident assessment of the hydro-ecological relationship at that location. Unlike linear mixed effects models, we're also able to extrapolate. We get a global relationship which allows us to predict our ecological response at new sites that don't have any monitoring data. Now, you could, of course, take a standard linear model and take that relationship and assume that it applies to another location, but that is an assumption. And if we're borrowing a relationship and applying it to a new location, we have no way of quantifying the effect of making that assumption. However, with the linear mixed effects models, because we've quantified the variability in the relationship from one site to another, we can explicitly incorporate that into our predictions and provide us a more quantitative measure of how confident we are at making predictions for new locations. Thirdly, linear mixed effects models are a little bit more efficient than standard linear models. They use slightly fewer degrees of freedom, one for the random intercept and one for the random slope. And so all else being equal, that gives these models a greater ability or power to detect statistically significant relationships. Fourthly, and really importantly, by explicitly including site as a factor in the model, then it means that we reduce the probability of getting false positive or false negative results, because we're accounting for the non-independence of the data, the fact that the individual sample measurements are nested within sites. That means we're getting reliable inferences. Moving across to the weaknesses column, these linear mixed effects models are a little bit more complex, as we've seen, and that brings with it more choices in terms of how we structure the model and also more assumptions that need to be checked. They are also a little bit more data hungry. As an absolute minimum, you need at least 5 different sites or sampling locations, and ideally a lot more, ideally 10 to 20, in order to get robust variance estimates. And if you're trying to fit models with random slopes, particularly if you've got random slopes for several different predictor variables, then you do need quite large amounts of data to be able to get reliable coefficient estimates and also to get your models to fit. You can sometimes encounter problems when you're trying to fit very complex models, with several different random slopes, for example, to your data set. If you don't have enough data, or if your sample sizes are quite unbalanced across the different sites, that is, some sites have a lot more data than others, then you will sometimes find that the models either fail to fit or will throw warning messages when you're trying to fit the model. Because we have both random effects as well as fixed effects in the model, then model selection can also be a bit harder. We have more choices about what the best model might look like. And finally, and like linear models, these linear mixed effects models do have a number of restrictive assumptions. So they are still assuming that the relationships follow a straight line, that they're linear. And also we are assuming here in these relatively simple models that the residuals from a model follow a normal distribution. So picking up on that final point, we've looked at a very simple example of where we have a standard linear mixed effects model. Quite a lot of biological response variables do indeed follow a normal distribution, and certainly in the modelling work that we've done with macroinvertebrate life scores and WHPT scores, those indices do tend to be quite well behaved. The residuals do follow a nice bell-shaped normal distribution. However, there are other data sets which certainly wouldn't follow that kind of distribution. So maybe we're dealing with presence-absence data, or percentage data that varies between 0 and 100. Or maybe we're dealing with count data derived from, say, an electric fishing survey, where we count the number of individual fish caught at a particular location. In all of those situations, we wouldn't expect the data to follow a normal distribution. However, the linear mixed effects models that we've just been looking at can easily be extended into generalized linear mixed effects models. These again provide a way of estimating the effect of flow and other fixed effects, whilst also allowing those effects to vary randomly from one site to another. So the key here is to define an appropriate error distribution that matches our data. So, for example, you might choose a binomial distribution for presence-absence data, a Poisson distribution for count data, or a negative binomial distribution for over-dispersed count data. Getting the right error distribution is really important because A, means that we get valid inferences, i.e. we get a useful model, and secondly, if we're then using that model to make predictions, it constrains the predictions to take valid values. So for example, if we were analysing presence-absence data, then it would ensure that the probability of occurrence is constrained to be between 0 and 1. And similarly, if we were modelling count data, the predictions could only ever take values of 0 or greater. You would never get a prediction of a negative count. The other way in which these models can be extended is to relax the assumption that the relationship is always a linear straight line. We can use two different modelling techniques: generalised additive mixed models and hierarchical generalised additive models. Both of these techniques allow us to model the relationship between the response and each predictor variable as a smooth curve. You can see an example on the slide here. This is taken from some work we did looking at invertebrate communities in sandstone streams in the Midlands. Here we've regressed life OE ratios against a measure of the Q75 flows in the previous 12 months. You can see from the plot that relationship is no longer a straight line, it's a curved relationship, and it indicates in particular that hydro-ecological relationship is steeper when the flows are lower, and it tends to plateau off at higher flows. So these more flexible techniques allow us to identify potential sort of threshold effects, for example, below which maybe ecological responses become stronger and more severe. It's a data-driven approach, however, so the degree of flexibility in the curve really is dictated by the data. You may get a very wiggly relationship, but equally, if the data do conform to a relatively nice simple straight line, then you will get a linear relationship coming out. So it really gives you the best of both worlds. So there's two different packages that you can use in R to fit these models: the GAM4 package and the MGCV package. Again, there's quite a lot of technical detail behind these methods, so I would encourage you to read up on these approaches before applying them. And again, I can provide some references for you to follow up on at the end of this workshop. That's been a very quick whistle-stop tour of mixed effects modelling. We've seen how we can build upon a simple linear regression model that's calibrated to a single site, and actually move things forward to take data from multiple sites and use a mixed effects model which fits both a global relationship but also has the flexibility to give us a site-specific regression relationship as well.